This is Kickass Politics. I'm Ben Mathis. Hi, folks. Before we start the show, I want to ask for your help. If you enjoy Kickass Politics, I hope you'll help us reach our goal of raising our full production budget for 2016 by donating on our website at kickasspolitics.com or at gofundme.com/kickasspolitics. Thanks for listening, and now enjoy the show. The Big Bang Theory, black holes, parallel universes, time travel. Today we're pushing the boundaries of what's possible as we explore where we came from and how far we may one day go. With my guest, theoretical physicist and futurist, the amazing Dr. Michio Kaku. He's a professor of theoretical physics at New York City College and the co-founder of string field theory, which he employs in his lifelong quest to complete the work that consumed the last 30 years of Albert Einstein's life, coming up with a simple 1-inch long equation that unites the four fundamental forces of nature into a single grand unifying theory of everything. He's the author of 8 books and 3 New York Times bestsellers, including Hyperspace, a scientific odyssey through parallel universes, time warps, and the 10th dimension. Physics of the Impossible, a scientific exploration into the world of phasors, force fields, teleportation, and time travel. Physics of the Future, how science will shape human destiny and our daily lives by the year 2100. And his most recent book, The Future of the Mind, the scientific quest to understand, enhance, and empower the mind. But he's most widely known as an acclaimed public speaker and popularizer of science. He's a science contributor to CBS This Morning, and he's appeared on hundreds of television programs. He's hosted several television series and specials, including a 3-hour special for the Discovery Channel called 2057, in which he explores what the next 50 years hold in store for us, a 3-hour documentary for the BBC called Visions of the Future, and his acclaimed television series for the Science Channel called Sci-Fi Science, Physics of the Impossible. Today, Dr. Michio Kaku will talk about his lifelong work to complete Einstein's unified theory, how his high school science fair project of building a particle accelerator in his parents' garage led to a scholarship to Harvard, and he'll discuss how the recent discovery of Einstein's gravitational waves may give us a window, in his words, into creation itself. Plus, he'll explain how spectacular inventions that were once the realm of science fiction may one day be science reality, including time machines, teleportation, force fields, starships, and even man-made wormholes that could transport us to an infinite number of parallel universes. Prepare to have your mind blown with my guest today, theoretical physicist and futurist, Dr. Michio Kaku. Coming up in just a moment.
Hollywood to Washington, it's time for Kickass Politics. And now here's your host, Ben Mathis.
My guest today is theoretical physicist Dr. Michio Kaku. He's a professor at New York City College. He's also the author of 3 New York Times bestsellers. He's the co-founder of string field theory. He's an acclaimed public speaker, renowned futurist, and popularizer of science. And his greatest achievement may be yet to come when he hopefully will complete Einstein's unified theory, also known as the theory of everything. Professor Michio Kaku, thank you for sitting down to talk to me.
Glad to be on your show.
Well, I'm going to start off. I'm going to give you a softball to begin with. This has been bothering me for a few hours this morning. Earlier in the morning, I was rummaging around in my desk drawer. I was trying to find something, and there was a battery. There was one of those 9-volt batteries. and it was blazing hot for some reason. It was just sitting in the drawer, almost to the point that it could burn you. And I couldn't figure out why. And I had AA batteries in the drawer. They were perfectly cool. Do you have any idea what was going on there?
Well, you have to watch out for lithium batteries because they tend to also, on occasion, explode, and they can bring down airplanes. In fact, is one theory, which I think is quite credible, that the Malaysian plane that went down in Asia that is still missing after many, many, many months and years of work probably went down because of a lithium battery fire. And in the cargo, you will have batteries that overheat. In fact, the U.S. government even issued just recently a warning stating, watch out, these lithium batteries will get hot, will explode, will create fires, and can actually bring down airplanes.
What is it that makes them get so hot?
There's a chemical reaction. Unfortunately, many of the batteries are built in China. Not to say that all Chinese batteries are deficient, but some of them are. And they are flooding into the marketplace. And unfortunately, we're getting more and more of these incidents where lithium batteries will sustain a chemical reaction, generating heat in an exothermic reaction, which will eventually cause a fire and perhaps an explosion.
Okay, because I had other batteries there, and they weren't hot. Is it? I didn't pay enough attention, I guess. Is it possible that those weren't lithium batteries then?
Probably all of them were lithium batteries,
okay.
But a fraction of them are defective. And this is causing concern with the United States government because of the possibility of a fire. Now, these fires have actually taken place in the cargo holds of airplanes. So far, we have not seen any airplane officially brought down by one. However, I think the Malaysian airplane was probably brought down by a lithium battery explosion.
Okay, so I better get that thing out of my office pronto.
I would say so.
Okay, well, shoot. Well, going on to the big stuff, your life's work has been trying to complete Einstein's unified theory, or a theory of everything. Now, I think that I have a pretty good grasp of the theory of specialized relativity and Einstein's theory of general relativity, but the theory of everything, I'm still having trouble grasping.
Well, the question is, what is everything? There are four fundamental forces that make the universe go. First is gravity, which holds the Earth together, keeps the sun from exploding, makes the solar system move. Second is the electromagnetic force, which lights up our cities, creates electricity, and so on and so forth. The third and the fourth are the weak and the strong nuclear force that lights up the sun. The problem is that these forces do not like each other. They have different mathematics, different formulations, and we want a single theory that can unite all four fundamental forces into a single framework. So far, the only candidate, because all other candidates have been shown to be inconsistent, is string theory. And that's what I do for a living. That's my day job.
Yeah, and you've said that string theory is pretty much the only game in town when it comes to trying to figure out this problem.
That's right. We think that when the string vibrates, it creates musical notes like a violin string, and each vibration corresponds to a subatomic particle. So if I were to get a microscope and look into an electron, I would see a rubber band. And when the rubber band twangs one way, it's called an electron. I twang it another way, it turns into a neutrino. I twang it a third way, it turns into a quark. And if you twang it enough times, it turns into the hundreds, the thousands of subatomic particles that we've been studying over the last 50 years. So all of that is nothing but music. So physics is nothing but the laws of harmony of vibrating strings. Chemistry is nothing but the melodies you can create on vibrating strings. The universe is a symphony of strings. And the mind of God that Albert Einstein eloquently wrote about for 30 years of his life, the mind of God is cosmic music resonating through 11-dimensional hyperspace.
So then would this give us a way to trace things back to the beginning?
That's right. We think that the original Big Bang was a bang in nothing, that is 11-dimensional hyperspace. Wow. And out of that quantum fluctuation came the Big Bang and the universe that we know. But you see, string theory even goes before the Big Bang. Einstein's theory makes no sense at the instant of the Big Bang. It just blows up. But string theory is a theory that goes beyond Einstein. And we can run the videotape before Genesis chapter 1, verse 1. And when we do that, we see that the universe may have had an umbilical cord as it emerged from the womb. And we think that it was connected to a multiverse of universes. And so if you take a soap bubble and that soap bubble is expanding, that's called the Big Bang Theory, commonly seen on CBS television. So the Big Bang is basically a bubble that expands, but we now believe there could be other bubbles out there, other universes. And when these universes collide or fission, that's called the Big Bang.
Well, Einstein spent the last 30 years of his life working on finding a theory of everything. And many people said that he probably should have gone fishing and just rested on his laurels for those last 30 years rather than going on what some people would say would be a fool's errand. Did that seem intimidating to you when you first set out on this process to try and finish his unified theory?
Well, when I first started this, I was 8 years old, and there was a famous picture that was flashed soon after Einstein died of his desk. And the caption of the picture said, "This is the unfinished manuscript from the greatest scientist of our time." Well, I was only 8 years old. I was mesmerized. I was hooked. I said to myself, this is for me. Why not try to finish this? What could be so hard that he couldn't finish this theory of everything? Well, I can read that book now. And when I read the book, I see all the dead ends. I see all the mistakes and all the avenues that didn't pan out. I can see where Einstein got stuck. Among other things, he got stuck on the fourth dimension. He introduced the fourth dimension, but he couldn't quite get his head around the fact there could be even dimensions far beyond 4. In fact, today we think that string theory allows for 11 dimensions. And in 11 dimensions, there's enough room to stick all the 4 fundamental forces. In other words, in our traditional 3 and 4 dimensional world, there's not enough room to fit the electromagnetic, the weak, the strong nuclear forces. In 11 dimensions, there's enough room to fit everything into a single theory. And so by reading Einstein's unfinished manuscript, I can see why he was so frustrated. Plus, back then, they didn't have the nuclear force. You can't blame Einstein. After all, the year was 1925 when he first began the unified field theory. Now we do have the nuclear force. And what comes out of the nuclear force? Strings. When we analyze what holds the quarks together, we see strings holding the quarks together. And so you see, you can't blame Einstein for not getting the unified field theory, because back in 1925, we knew almost nothing about the physics of the universe.
Yeah, and we didn't have computers and so much technology. I mean, you've said that scientists are still winning Nobel Prizes, just making giant technical leaps from the theories of Einstein 100 years ago, just working on the crumbs of his ideas. One of the big ones only just recently happened, was about a month ago. The scientists from MIT and Caltech working on the LIGO project announced that they had proven the existence of gravitational waves, which were theorized by Einstein over 100 years ago. You said this opens up a window on creation itself. What exactly do you mean by that?
Well, we now realize that there was 2 black holes which collided 1 billion years ago. The shock waves finally reached the planet Earth, measured by the LIGO experiment. However, in the future, we're going to put LIGO into outer space. It's called LISA, Laser Interferometry Space Antenna, and it's a new kind of telescope, a telescope that can pick up vibrations not just from colliding black holes, but from the creation of the universe itself. Now, we have baby pictures of the universe about 300,000 years after the explosion. Sure enough, it's an explosion. Go to nasa.gov, look under Kobe, and you can actually see the explosion from the Big Bang. But it's frustrating. These pictures are 300,000 years after the incident of the Big Bang. We want baby pictures of the universe as it emerges from the womb. For that, you need gravity wave telescopes, not optical telescopes. And that's why we want to put LIGO into outer space. LISA will then detect radiation from the Big Bang, the instant of the Big Bang. Then we run the videotape backwards. By running the videotape backwards, we can now detect what the radiation must have been before the Big Bang. And then we can rule in or out many of the string theories which predict what the universe looked like before the Big Bang. So I say to people who are cynics that we'll never be able to detect the presence of parallel universe, no. Using gravity waves, we will be able to have pictures of the umbilical cord that connects our infant universe to another universe.
Wow. And then what would be perhaps some of the applications of this?
Well, the
Where
Big
could this
Bang,
lead
of
us?
course, happened only once in our sector of the universe. However, we do think it happens over and over again in other sectors of the multiverse. But maybe one day when we become advanced enough, we'll be able to create our own mini black hole. In which case, you can't rule it out, we might be able to drill holes in space and perhaps take shortcuts throughout the universe. These are called wormholes, first introduced in the popular literature in a book called Alice in Wonderland. In Alice in Wonderland, Alice sticks her hand through a mirror and her hand winds up in Wonderland. Well, that is what we physicists call a multiply connected space, i.e., a wormhole. That is a gateway, a porthole, an entrance between two universes. And so this is something that we physicists take very seriously.
Yeah, and now we're getting into the other side of your career, which is you had two heroes. You had Einstein, who we already mentioned, and who was the other hero who's inspired this new phase in your career?
Well, my first hero was Albert Einstein. I wanted to help complete this unfinished manuscript that I read about when I was 8 years old. But every Saturday morning, I would watch Flash Gordon on the morning TV set. And for the first time in my life, I saw starships. I saw aliens, ray guns, cities in the sky, invisibility machines. I was hooked. I mean, I said to myself, this is really neat stuff. But later, I began to realize something. To really understand ray guns and invisibility shields and cities in the sky, you have to be like Dr. Zarkov. You have to be a physicist. Years later, I began to realize that Dr. Zarkov, the man who created the starships, who created the cities in the sky, he was a physicist. I didn't even know what the word was, but it helped to propel me in the direction of becoming a physicist.
Yeah, and one of the things that you were just talking about, the wormholes and black holes, that seems to be a lot of the key to some of these huge, crazy ideas, maybe way down in the future. You know, time travel, parallel worlds, even making huge leaps through space to other galaxies and so forth. How would that work? We would create a wormhole artificially, or are we talking about actually going into a black hole?
Well, first of all, we don't know, but we have the mathematics to lead us the way.
That's honest of you.
Right. So first you start with enormous amounts of positive energy in the form of a black hole, a colliding star, a colliding black holes. You talk about tremendous amounts of positive energy, sufficient to open a gateway, a hole in the fabric of space and time. But these fabrics, these holes in the fabric of space and time are unstable. They don't last very long. If you watch Star Trek, for example, they always talk about the instability of the wormhole. So you have to stabilize it. And you stabilize it with something called negative energy. Negative energy is very exotic. We've actually created negative energy in the laboratory via something called the Casimir effect. We did that, in fact, decades ago. So it is possible to stabilize a black hole or wormhole using negative energy, but we can only create minute quantities of it in the laboratory. It would take an advanced civilization, much more advanced than ours, to create large quantities of negative energy. So what you do is, A, you assemble lots of positive energy in one area to open a gateway. That's a black hole. Then B, you insert negative energy to stabilize it so the hole doesn't scrunch and kill you when you go through the gateway. So that's how you would open up a gateway through space and time, and that's how you would stabilize it.
And negative energy, is that the same as negative matter?
Well, matter and energy are the same in Einstein's
okay.
theory. Negative matter or negative energy falls up. It doesn't fall down.
Right.
Now, we've never seen that before. I've never seen something fall up before. But, however, negative energy has been actually created in the laboratory. We play with it. Using nanotechnology, for example, many nanotechnologists using tiny microscopic tweezers actually manipulate negative energy. So it's not science fiction. What is science fiction is to harvest enough negative energy to then keep the gateway from closing in on itself. And then you could, in fact, perhaps walk through the wormhole and wind up in Wonderland.
Well, we'll take a quick break, and then I'll be back with more with Dr. Michio Kaku. Back in just a moment. If you're enjoying my conversation with Professor Michio Kaku, then you'll love his books Einstein's Cosmos and Physics of the Impossible. And right now, you can download the audio versions of these books for free with a special promotion for our listeners from Audible.com. Just go to audibletrial.com/kickasspolitics for a free 30-day trial and a free audiobook download, which can be Einstein's Cosmos, Physics of the Impossible, or a number of other books by my guest today, Dr. Michio Kaku, plus any of Audible's 180,000 titles. That's audibletrial.com/kickasspolitics. Or click on the sponsor link on our webpage to download the free audiobook of your choice. And now, back to the show. We're back, and I'm talking with Professor Michio Kaku. In reading some of your books about what might be possible in the future, when we're talking about time travel or space travel, teleportation, it seems to me that so many of these innovations are theoretically totally possible, but it's entirely dependent on being able to have enough energy, enormous amounts of energy to power these things. Is that much of what will drive the future of innovation?
Well, let's talk about the far future, and then let's talk about the near future. We physicists rank civilizations on the basis of energy when we scan outer space looking for aliens. We rank them not by being little green men, but we rank them by energy. We call them Type 1, Type 2, and Type 3 civilizations. A Type 1 civilization harvests all the energy that falls on it from the sun. They can, for example, control the weather. They can control earthquakes and volcanoes. Anything planetary, they can control. Eventually, they exhaust the power of a planet and they begin to mine the sun. They use the sun as a battery, basically, to power their engines. Eventually, they get tired of using up the energy of the sun and they go through the galaxy. That's Type 3 when you start to have galactic energy. So Flash Gordon, the hero of my youth, would be living in a Type 1 civilization. Captain Kirk of the Starship Enterprise would be living in a Type 2 civilization because they can manipulate a few stars. Type 3 would be the Empire of The Empire Strikes Back. That would be a Type 3 civilization. Now, to harness the power of a black hole, you have to act something called the Planck energy. The Planck energy is enormous, 10 to the 19 billion electron volts. That's much more than the energy in our Large Hadron Collider. That's basically the energy of a Type 2 or perhaps a Type 3 civilization.
And where would antimatter fit into that? Because that goes back to your earliest days, how you got into science. You tried to create antimatter.
That's right. In fact, when I was in high school, I photographed antimatter for my science fair project. I went to the Atomic Energy Commission back then, got sodium-22, put it into a Wilson cloud chamber, 600 Gauss magnetic field, and I photographed gorgeous, absolutely gorgeous photographs of anti-electrons in my cloud chamber. And that took me to the National Science Fair, where I met a physicist who took me under his wing and sort of became my mentor. He arranged for me to get a scholarship to Harvard. And that was Edward Teller, the father of the hydrogen bomb.
Yeah, and antimatter, is that our best hope for, these ideas of spaceships that could go through a black hole and that sort of thing? Is that what we would need to power that, or is there something beyond that we would need?
Well, first of all, antimatter does exist. It wasn't discovered by Gene Roddenberry on Star Trek. It does exist. I played with it when I was in high school, but they're minute quantities of it.
Right.
To create large quantities of it, it would require a particle accelerator that it would exhaust the energy of the planet Earth. So we don't expect to create a antimatter engine being a Type 0 civilization, which we are today. But once we become Type 1, that is in 100, 200 years, once we become a Type 1 civilization, then it's well within the economic capability to create starships powered by antimatter. Now, I personally think that perhaps the first starships may actually be the size of needles. That is nanotechnology creating robotic needles that you send by the trillions into outer space, each one costing a fraction of a penny, and hopefully a few of them will reach Alpha Centauri. And you can accelerate them to enormous velocities because they're needles. In other words, we've been brainwashed by Star Trek into thinking that a starship has to be huge and gigantic. No, using nanotechnology, molecular spaceships may be created that can hurl near the speed of light. Think of that, near the speed of light, and using electric and magnetic fields that are found on the planet Earth. So I think the first starships may not look like the Enterprise at all. The first starships may be basically a mist of needles, nanotechnology robots that are sent near the speed of light into the heavens.
Yeah, and we were saying that so many of these things are dependent upon being able to produce enough energy to make them happen. It seems to me the other thing that a lot of these ideas are dependent upon are either being able to build on a massive scale or a very, very tiny scale. With nanotechnology, are we much closer to being able to do the little stuff than the big stuff these days?
Yeah, in fact, the most mathematically efficient way to explore the galaxy is not to send Captain Kirk on a starship looking for a Class M planet. That is the silliest way to explore the universe. The most efficient way is to create von Neumann probes. Von Neumann probes are small, they're self-replicating, they land on a moon, and they make a copy of themselves. They make a factory on the moon to create millions of copies of themselves, and they shoot out and they colonize millions of other moons which are stable. And starting with one von Neumann probe, you get 1 million, then 1 million million, and then 1 million million million. And pretty soon you have a sphere of trillions of von Neumann probes colonizing the galaxy near the speed of light. Now, you've seen that before. There's a Hollywood movie which actually explored this possibility called 2001. Kubrick's 2001 is actually the most realistic encounter with intelligent life in outer space. Really? In other words, on our moon, there is a small chance that there is a von Neumann probe, a self-replicating robot on our moon, just like in the movie, that is just waiting for us to make contact with it. And if you remember in the movie, there were billions of these probes surrounding Jupiter. Jupiter is the relay station that connects the Earth to the home planet. And so the next time you see 2001, see it through the minds of a physicist, that it is perhaps the most realistic encounter with extraterrestrial intelligence, and they're already here.
I'm intrigued by all of this. In envisioning these inventions of the future, such as teleportation, it's a similar concept where a lot of these things are sending the information somewhere and reconstructing them. You talk about it would be the data that we would send. It wouldn't be our actual physical matter if we were to teleport.
Well, there's several ways you might be able to zip across the galaxy this way. One is called quantum teleportation, which we actually do in the laboratory. We've actually teleported photons, atoms of cesium, rubidium, in the laboratory several hundred yards. In fact, for the Science Channel, I even took a film crew to the University of Maryland, and we photographed this process on camera. And you could actually see the records of atoms being teleported from one part of the room to the other part of the room. But hey, let's be real. To teleport Captain Kirk would require technology that is centuries ahead of us. But in Star Trek, hey, that's in the 23rd century, so we still have a few centuries to go. Yeah. I think there's another way to do it, which is more practical, and we might be able to do it within maybe 100 years. Really? And that is to shoot our consciousness throughout the universe. We're going to have something called the Connectome Project. It's going to be perhaps bigger than the Genome Project. The Connectome Project is being funded by the Obama administration. And $1 billion are going to be spent to map the human brain. Once we have a complete map of every neuron of the human brain, we could put that on a laser beam. All that information can be placed on a laser beam and then shot to the moon. This is perhaps the most efficient way for space travel. In other words, our consciousness, our memories, our desires, our feelings could be put on a laser beam because of the Connectome Project, shot to the moon, and we'd be on the moon in 1 second. No booster rockets, no weightlessness, forget all that. Wow. No micrometeorites. To go to Mars would take 20 minutes. To go to Alpha Centauri, the nearest star, would take 4 years. And what do we put on the moon? We would put a robot on the moon that could receive all the information of our connectome, and our consciousness would be then installed in a robot on the moon.
Wow.
This is perhaps the most efficient way to explore the galaxy. Our consciousness shot on a laser beam, reassembled on the moon, reassembled on Jupiter or wherever, and then we would become Superman on the moon or Jupiter. We could breathe noxious gases, work in horrible magnetic fields, electric fields, because we are resurrected in the body of a robot, guided by the connectome, which is inside the brain of the robot. Now, you may say to yourself, well, it'll take at least 100 years for us to do that, but maybe it already exists. Aliens from outer space may say to themselves, the most efficient way to explore the universe is to send our consciousness throughout the universe on a laser beam via the Connectome Project, currently funded by the Obama administration, and then reassemble our consciousness on distant planets as robots to wake up as Superman. Now, how long would it take? You would essentially go to sleep and wake up instantly on a distant star. You would have no memory of the fact that you just spent 100 years traveling 100 light years to a star that is trillions of miles distant. Maybe this already exists. Maybe there's already an intergalactic highway system, and we humans are too stupid to know it.
So there may be aliens who are visiting us, and we're just not aware of it.
That's
because
right.
We can't see them physically.
I don't want people to get paranoid, but when we become sufficiently advanced, like in 100 years, we're going to have the Connectome Project map all the neurons of the brain, and we can put that on a laser beam. We could do that today, in fact, and we could shoot it to the moon. This is the most efficient way to explore the universe without booster rockets, without micrometeorites, without radiation, without weightlessness, no Van Allen belt to worry about, none of that. Pure energy containing information shot throughout the universe. And this is something out of Isaac Asimov, but I think it's well within the laws of physics.
Yeah, and you said that we would be able to send the data on a laser beam and reconstruct ourselves.
Right.
From molecules that are already there, because we have, in theory, we would have the building blocks wherever we might be.
Right. Now, of course, the first generation to go to the moon and Mars and so on and so forth would have to create the base. You would have to have a factory that produces robots that are waiting for consciousness to be downloaded into their memory circuits. So that is a bottleneck. We would have to, the first generation would have to create the base.
Someone has to take the risk.
Someone has to take the risk.
Okay.
Once the base is set up, it could receive signals from laser beams shot from the planet Earth, and then you could reassemble people's consciousness on a distant star.
Wow. Well, another thing that you've talked about is how to build a force field, like something out of Star Wars. It's basically creating a shield out of nothing. How would something like that work? Would it be similar? Would it be somehow rearranging molecules into something hard?
Well, let's talk about Buck Rogers in science fiction.
Okay.
In Buck Rogers in science fiction, you have jetpacks, you have flying cars, and you have force fields, and you have ray guns. And then people ask a simple question. How come we don't have ray guns, force fields, jetpacks? How come we don't have them? And the answer could be summarized in one phrase. We don't have a portable power pack. We can create a jetpack just like Buck Rogers, but it only lasts for a few minutes because of the lack of a portable power supply. We can create a ray gun energized by a nuclear power plant with the power of Buck Rogers' ray gun. But that means you have to have a nuclear power plant sitting on your back to energize your ray gun. And the same thing with force fields. So the problem is a portable power pack. Now, in science fiction, it's boring to talk about portable power packs. But if you want to create science fiction things turn into life, you have to face the fact that we don't have. We do not yet have a portable power pack sufficient to drive force fields, power packs, flying cars. But we could do it. But we simply do not have the miniaturization project. Now, of course, hydrogen bombs is the largest source of power accessible to Homo sapiens, but hydrogen bombs are also highly unstable and will blow you up as well as the enemy.
Yeah, I don't want to try that one.
Right.
So, okay.
But yeah, we have flying cars. They're just extremely expensive and impractical at the present time.
Yeah, and then it does all go back to energy.
Energy.
Things that are possible if we could just figure out how to create
and
smaller...
miniaturize it so you could put it inside a ray gun.
Wow. Well, let's talk about one of the big ones here, time travel.
Mm-hmm.
Now, your friend Stephen Hawking, he has said that if time travel were possible, why aren't tourists from the future constantly inundating us, and why isn't history changing all the time? How do you answer that?
If history is changing all the time, we would never know it.
Okay.
Because our memories change too. So maybe history is being changed all the time, except we're too dumb to know it because our memories, circuits, are changed in the process. Well, first of all, I think that time travel is centuries away, but we will have things like invisibility perhaps within this century. So maybe the aliens who are using time travel to visit us, maybe they're invisible. Maybe they're already here. We're just too stupid to know it because we will have invisibility centuries before we have time travel. Now, if you were to ask Stephen exactly what is your objection to time travel, he'd be the first to say that Einstein's equations do admit wormholes. They do admit gateways into the past. Physicists have seriously taken these gateways to the past and worked out the mathematics. The problem, he would say, is that radiation. Radiation builds up as you enter the time machine, and the time machine blows up, and therefore you cannot go backwards in time. However, I've looked at his calculation. His calculation is only halfway there. He assumed that the radiation that comes out of a time machine is the radiation of matter, that is electrons, neutrons, and protons. But there's also the radiation of gravity. We see that with gravity wave detectors. We know that gravity waves exist, and that's a form of radiation. So you have to have a quantum theory of gravity, and that's string theory. Unfortunately, Stephen does not do string theory, mainly because he's physically handicapped. And to do string theory, you have to have access to your hands to do hundreds of pages of calculations. So unfortunately, he cannot work on string theory, though, of course, he's had conferences on string theory at his laboratory. In fact, I spoke at one of his conferences on string theory at Cambridge. So when you go to string theory, all bets are off. At that point, it may be stable. We're not sure. It may be stable to go through the wormhole. And so all the calculations showing an explosion are due to the fact that you're only taking half the calculation. You're throwing away gravity waves. Gravity waves do not exist in Stephen's calculation. I can't blame him, of course, because to do that, you have to have string theory, which is what I do for a living.
Well, as I understand it, in theory, it would be a lot easier for us to go to the future than to actually go backwards in time, especially with any specificity.
Right. When you go to Jupiter, for example, in some sense, you become a time traveler. For example, on the moon, time beats a little bit faster on the moon than it does on the Earth. Time beats slower on Jupiter than it does on the planet Earth. And your GPS in your cell phone calculates this all the time. You would get lost on a camping trip unless you take into account the fact that time beats slower on a satellite going overhead. So going backwards in time, that's the big one. Because if you go backwards in time and you commit suicide in the past, how can you be alive today to commit suicide in the past?
Right. Or how can you be alive if you, hooked up with your mother back in the past, like Back to the Future?
Right. Now, there is a solution to this.
Okay.
And the solution, again, comes from string theory. And that is, string theory is a quantum theory. Quantum theory deals with multiple universes. And so when you go backwards into the past to meet your teenage mother before you're born, you've met another girl who looks like your mother, has the same memories as your mother, the same DNA as your mother, but is actually a parallel mother. The universe splits in half, and you wind up in a different timeline. Now, if you saw the second Back to the Future Part 2, Doc Brown goes to the blackboard and draws a horizontal line and says, that's our timeline. Past on the left, future on the right. And then he draws a fork in the river of time and says that's when Biff the bully starts to monkey with the past. That's what string theory would say. String theory says that the universe splits in half, a quantum mechanical split. So if you save Abraham Lincoln from being assassinated in the Ford Theater, that's somebody else's Abraham Lincoln. Your Abraham Lincoln died. That cannot be changed. Okay. But you've saved somebody else's Abraham Lincoln from being assassinated at the Ford Theater.
Okay, so it gets into parallel universes.
That's right.
Then. Okay.
That's right. In fact, one of the main reasons why some people don't like string theory is precisely that. That string theory inevitably takes you to 11-dimensional hyperspace and parallel universes. And some people, for philosophical reasons, don't like that.
Huh. Well, before we go, I'm curious if you borrow anything else from Einstein. For instance, today, in his and your honor, I'm not wearing socks, as you can see. Einstein didn't wear socks. He always pretty much wore the same thing, sometimes didn't shower or comb his hair. And when he was looking for a breakthrough, he would play his violin. Do you have anything that you borrow from him or anything that's just yours?
Well, when I was a kid, I read those stories about how strange he was. But I also read another quote, and that was, he says, "Do not look at the man that I appear to be. Look at the man that I aspire to be." That is the man that is in his thoughts. So I said to myself, yeah, of course he may be a little bit eccentric about his socks and his shoes and his pipe and his sweatshirts and things like that, which are iconic. But he says, don't look at the man you see. Look at the way he thinks. The way he thought was in terms of pictures and diagrams and principles and concepts. The rest is algebra. The rest is just mathematics to him. Bookkeeping to him.
Interesting. Do you have anything like your version of the violin?
Well, one thing that I do that really clears the head is figure skate.
Right.
And when you're on the ice, it's just you and Isaac Newton. All the clutter of friction and all the messiness of the physical world are eliminated, and it's just you and pure Newtonian law.
Interesting. So do you get more work done in the winter?
No, but it's nice to think about it because it clears the mind and you begin to really feel at home with the universe.
Yeah.
See, the universe looks very cluttered. The universe looks messy. How can you possibly make sense out of the clutter that you see around us? And then you're on the ice rink and you realize that it's really simple. It's clean. It's elegant. A handful of physical laws govern all the clutter that you see around you.
Amazing. Okay, so if you want to be a genius, ice skate. Well, folks can also submit their theories for finishing the unified theory to you also, but you'd probably prefer that they not, I imagine.
I prefer you send it to Physical Review D and Nuclear Physics B and earn all the accolades when you finish Einstein's theory. So publish the results in a physics magazine, Nuclear Physics B or Physical Review D.
Okay. Well, Dr. Michio Kaku, thank you so much.
My pleasure.
Thanks again to Professor Michio Kaku for coming on the show. This is just part one of our conversation, and in the next episode, we'll get into the science of the near future, discoveries and inventions that will change everything within our lifetime, some of which may be as little as 5 years away. I'm talking about computers that fit into a contact lens, invisibility cloaks, uploading a whole college course directly to your brain, or downloading your entire consciousness to a microchip. Never dying of cancer, and maybe never dying at all. Plus so much more mind-blowing technology that will completely change our lives within the next few decades. So be sure to download the next podcast. If you enjoyed today's episode, you can follow Professor Michio Kaku at mkaku.org. That's mkaku.org. Or you can follow him on Twitter at Michio Kaku. You can also subscribe to his weekly podcast on iTunes. It's called Explorations in Science. Or if you go to his site, you can find a list of stations that carry his weekly syndicated radio show called Science Fantastic. I'd encourage you to read some of his books, especially Einstein's Cosmos, Physics of the Impossible, Physics of the Future, and The Future of the Mind. If you liked our conversation, these books are beyond interesting. So I'll include Amazon links where you can order those and other books by Michio Kaku in the show notes for this episode and on our website at kickasspolitics.com. And if you prefer to listen to the audio versions, you can download those for free through that special trial offer just for our listeners at audibletrial.com/kickasspolitics. Now, folks, don't forget to subscribe to Kickass Politics on iTunes and leave us a review. That helps a bunch with our podcast rankings. And if you really want to help us out, then donate to our GoFundMe campaign at gofundme.com/kickasspolitics. Or click on the donate button on our website at kickasspolitics.com. Your support is always appreciated. Follow us on Twitter at @a.k.a. politics, or visit Kickass Politics on Facebook. And while you're there, recommend Kickass Politics to your friends on your social media. And as always, I welcome your comments, questions, and suggestions at comments@kickasspolitics.com. Once more, don't forget to download the next episode, which will be part 2 of my conversation with Dr. Michio Kaku. We'll talk about very recent advances in science that will change your life within the next few years. You're really not going to believe some of the stuff that's coming up, so be sure to tune in to part 2. But for now, I'm Ben Mathis, and thanks for listening to Kick-Ass Politics. Kickass Politics is a trademark of Mathis Entertainment, Inc.